Welcome back. Let's start with the fact here. If f is continuous and non-zero on the interval from a to b, then f cannot change sign on this interval. So what we are saying is that if f is continuous on the interval from a to b, and if f of x is not equal to 0 for any x between a and b, then either f of x is positive for all x between a and b, or f of x is negative throughout the interval from a to b. So that is, on this interval from a to b, the function doesn't change sign. Now, why is that the case? Well, if f has both a positive and a negative value in this interval, then part of the graph of f would be above the x-axis, and the part of the graph of f would be below the x-axis, right? Since it has both positive and negative values. But since f is continuous, because f is continuous, the graph then must cross the x-axis as it goes from positive to negative or negative to positive values. So the graph must cross the x-axis, but then f would have a 0 at some point between a and b, but we are assuming that f has no zeros in between a and b. So you can see why f must have a constant sign on this interval where it's continuous and non-zero. Okay, let's look at the question. We want to solve x squared minus 2x greater than 0, and that is, we want to find the values of x for which the polynomial x squared minus 2x is positive. Factoring, we can factor the polynomial here, and we get x times x minus 2, and so the inequality, given inequality, is the same as the inequality x times x minus 2 is greater than 0. We see that the polynomial is 0 when x is 0 or when x is 2. And the zeros of this, the domain of this polynomial is the set of all real numbers. And the zeros of this polynomial divide the x-axis or the number line into 3 subintervals. So one from negative infinity to 0, one from 0 to infinity, and another from 2 to infinity. So if I know the graph, if I draw the graph of this polynomial, I get this parabola. And looking at this graph, we see clearly that this polynomial is positive when x is less than 0, that is, when x is in the interval from negative infinity to 0, and when x is bigger than 2, that is when x is in the interval from 2 to infinity, the polynomial is positive. So we see that this inequality is true when x is in the interval from negative infinity to 0, union 2 to infinity, open parentheses at 0 and 2 because they are not included. Now, how would we do this if we didn't have the graph? So without the graph, how do we do it? Well, so if I didn't have the graph, so the thing that I'm going to do here is that, okay, I know where this polynomial is, I know all the values of x where the polynomial is 0. So the polynomial is 0 when x is 0 or 2. So then the x-axis or the domain of this function can be divided into 3 subintervals like this. So we divide the number line at 0 and 2. We get these 3 subintervals. And now the polynomial has no zeros in each of these subintervals. So the polynomial doesn't change sign in each of these subintervals. So let's figure out the sign of the polynomial in the first interval here. Well, in this interval, I have the point -1. So if x is -1, what is the sign of the function here? So if x is -1, I get -1 here. -1 minus 2 would be -3. So I get -1 times -3. Well, that's positive. So I see that this function is positive when x is -1. But f has no zeros here in this interval. So f doesn't change sign here. So therefore, since it is positive at one point, it's got to be positive throughout. So this polynomial is positive here. Similarly, you'll see that it is positive here because if I take x to be 3, then 3 times 3 minus 2 is positive. So this polynomial is positive at 1.3 here. Since it doesn't change sign here, it must be positive throughout. Now, in this interval, if x is, if I can pick the number 1, plug in 1 here, we get 1 times 1 minus 2, which is 1 times -1, which is negative. So we see that this function is negative at 1. Since it has no zeros in this interval, it cannot change sign here. So if it is negative at one point, it's got to be negative throughout this interval. So we see that it's positive here, negative here. And so it is positive on the interval from -infinity to 0, union the interval from 2 to infinity. Okay, without graphing, solve this inequality. Here we have a rational function. To figure out where it is positive, that is, we want to figure out the values of x for which this function is positive. So first thing we're going to do is we're going to figure out where the function is undefined. So the function is undefined when x is 3. So the domain of the function is the interval from -infinity to 3, union 3 to infinity, excluding 3, of course. And then let's notice that the function f would be 0 wherever the numerator would be. So if I have a fraction, the fraction is 0 when the numerator is 0. So the numerator here is 0 when x is plus or minus 1. So we see that the function f has 2 zeros, one at -1 and the other at 1. Now, this -1 and 1 will not be in the solution of this inequality because this is not greater than or equal to, this is strictly greater than 0. If I had greater than or equal to 0 here, then -1 and 1 would satisfy this inequality. Okay, so then the x-axis or the number line, on the number line we're going to draw the zeros of the function and the points where the function is undefined. So here are the 2 zeros and here is where the function is undefined. So these 3 numbers, we're going to call them the partition numbers for f, and they divide the number line into 4 subintervals, and f has no zeros on the left of -1, f has no zeros strictly in between -1 and 1, f has no zeros here, f has no zeros here. So f doesn't change sign in each of these intervals. So on each interval, either f is positive or negative throughout the interval by the continuity of the function f. So to figure out the sign, then we just test a number from each interval by plugging it in into f. So let's do that. So this is the function f, and let's figure out the sign of f at, let's say, -1, -2. F of -2, it would be -2 squared minus 1 over -2 minus 3, which is 3 over -5, which is negative. So f is continuous on the left side of -1. F has no zeros on the left side of -1, and therefore f doesn't change sign on the left of -1. Since it is negative at a point, it's got to be negative throughout this interval from -infinity to -1. So we just do the same thing in each of these intervals now. So we see we just found that f is negative on the left side of -1. In between -1 and 1, well, the number 0 is there, so let's plug that in. F of 0 would be 0 squared minus 1 over 0 minus 3, which is positive. So we see that f of x is positive throughout the interval from -1 to 1. Between 1 and 3, we can pick the number 2, plug that in. We get 2 squared minus 1 over 2 minus 3, which is negative again. So we see that f is negative throughout the interval from 1 to 3. Lastly, we take the point 4 in the last interval here, and if we plug in, we get positive again. So if I plug in 4, I get 4 squared minus 1 over 4 minus 3. That's 15 over 1, which is positive. So we see that f of x is positive on the interval from 3 to infinity. So this is what we got. So then that f is positive between -1 and 1, and it is positive after 3. So f is positive on the interval from -1 to 1 union the interval from 3 to infinity. Open parentheses at 1 and 3 because they are not included in the solution. Okay, so we will stop the video here, and in the next video we will be solving another problem.